happens when we go into 3 dimensions, because that really is what kind of starts getting us looking at things. So one of the first things that happens is if we have something in 3 dimensions, right? And this is where isometric paper really starts to help you out. And I'm going to ditch this marker because it's already dead. It's that time of the year. It's that time of the semester. All right, so I've got my 3 dimensions, and we've got whatever object we have that we're going to play with or spin or rotate or do whatever with. You can actually look at this and think of a spherical coordinate system, okay? So one of the things you can do is change your coordinate system. And remember, my spherical coordinate system is going to have an R, and then there's like if this is a Z axis, and this is my Y axis, and this is my X axis, you get this angle from the YZ axis, and then you get this angle from the XZ axis, and one's a phi and one's a theta. Or you can do more the cylindrical type coordinates, and you can do your Z, and you have your other angles as well. So you can do your projections. So that's one way to look at what's happening. And so if you think about it, things that would end up working like this is if you've got a track hoe of some sort or a crane, and you're moving your crane around a fixed position, you're going to want to use cylindrical or spherical coordinate systems. So we can look at it from that perspective. But we can also look at it as if I have my object and I have my point A on my object, and then I have another point B on my object, and I've got a rotation that's going around here for A. I also can have this, and then I have my object B, and then I've got an RBA, which is something that we've been working on for our 2-dimensional systems all along, but but things get a little more complicated when we move to 3 dimensions. So let's move to 3 dimensions and kind of look at the translational motion associated with it. So if I've got that object like this, and I've got it rotating about, and this is my point A, here's my point B, here's my RBA, and then I've got an angle here. What ends up being is that the relative motion from B to A is going to be our angular vector crosswise with our radial vector BA. And if we go ahead and move on to my ABA, we get our crosswise. Cross product. And as you might suspect, things are going to start to get a bit gory. Because now we're keeping track, and these, of course, are our kinematics, and these are cross products, so we're having to keep track of a variety of things. And remember that the absolute motion so if I look at the absolute motion of B, it's going to be the velocity of A plus my velocity B to A. And if I look at the acceleration, the absolute acceleration, I'm going to get my acceleration plus my acceleration B to A. So we get that relative motion. So let's take a problem to look at it to see how this is going to work. See if I can draw a good picture here. We draw pictures. So I've got a rod. On this rod, I have a collar. okay? So that my collar can rotate around my rod. And it's going to be rotating around the collar at an omega 1. So we're going to have it rotate around the collar. Connected to this collar is a rod with a disc on the end. And this disc is free to rotate. And it's going to be rotating around the rod with an angular velocity of omega 2. The rod has a length of L. The disc has a radius of R. We're going to use the collar as the origin. We're going to call the center about the axis that my disc is rotating A. And we're going to need it in a little while, but we're going to have a point P on the edge of the disc. To start with, we're going to ignore P, but right now we're going to start with that edge. So if I write out in my vector notation, omega 1 is going to be omega 1 in the K direction, and omega 2 is omega 2 in the J direction. So I've got my vector components. What we want to do is we want to determine, or what we're headed to do, is we want to determine the angular velocity of the disk and its angular acceleration for the system shown. So basically what we have is a wheel that's turning while this thing is rotating around. Okay? Wheel that's turning while it's rotating around. And you can think about this, if you've ever done sights on a turret, that's exactly what's happening. I've got a crank that I can be rotating around, and I'm going around in a circle on a turret.
What is a turret?
Top of a tank, something that rotates around. A turret's going to be top of a submarine, doing something. A lot of these things, if this is a crank that's going to move a telescope, something that's moving around on a turntable that I've got a crank that may be cranking in there. So there's a bunch of other things that I could be working with. So that's what we're going to do. So the angular, so if we're going to look at it, we're looking at it from the disk. So the disk is rotating like this, but at the same time it's rotating around the circle. So its fundamental angular velocity is going to be the angular velocity of 1 plus the angular velocity of 2, because I could add vectors to get a resultant vector. So if I do that, and we know what those angular velocities are, I'm going to get that's going to be my angular velocity of the disk. So I haven't done anything complicated yet, right? So that's my angular velocity of the disk. But now if I want to do, go ahead and do my dv/dt, and I'm going to do it with respect to my x, y, z coordinate system as I have it done shown. And this is just remember we showed this way back when. If I've got a rotating system, I can do this angular rotating reference crossed with the velocity vector. And we could get that back. And basically what that showed us, and we actually did this, and we went ahead and simplified it for 2 dimensions, that you end up with this in relationship to our stationary reference frame plus this cross product that I had for my other reference frame. So if I do this with a stationary reference frame, if I'm doing my omega dot with my stationary reference frame, that's just 1J plus 2K. But now we got to deal with this puppy that we have to work with. And it turns out that this, for this system, this is just omega 1 for this system. So now I have omega 1 cross with omega, and that's going to be omega 1K cross product omega 1, no, oh sorry, that's actually omega 2. This is omega 2. Yeah. No, that's right. That's right. That's omega 1. Sorry, that's omega 1. Omega 1K, that's omega 2. I've got these backwards. That's I, because I was going, wait a second. That is correct. Got to keep your subscript straight. So, omega 1, omega 2, and that's K cross J. And this is omega 1 squared K cross K. So that goes to 0. So I get minus omega 1, omega 2, I. So now my alpha is just going to be this omega 2j dot plus omega 1 dot k minus omega 1 omega 2 I. And you can rewrite it in whatever order makes you comfortable. All right, now we're going to go back and we're going to look at this P. So using this same system, we want to find the velocity and acceleration of P. Okay, so we're going to need a few pieces of information in order to do that. First, we now, for the disk, we know that omega is omega 1K plus omega 2J. And this is the disk. And alpha of the disk is omega 1K. Oh, I forgot to put the dots. Dots, omega 2 dot J minus omega 1 omega 2 I. So this is of the disk. But P related to A. So we're going to look at the motion of P related to A. So I'm going to get the velocity of A is going to equal omega 1 cross product RAO. So my velocity of A related to how it's going around O is going to be that right there. RAO is just LJ, where L is the length of the rod. So right now these are all in vector form. So omega 1 is a k, cross product, and there's my cross product Lj. So I'm going to get omega 1L k cross j, which gives me a minus omega 1L in the I direction. And my acceleration of A, this is where things get really fun, right? It's omega 1, time derivative of omega 1, RAO plus omega 1 crossed with omega 1 crossed with RAO. And everybody feels like they're in calculus class at this point. Vector calculus class at that. Well, we already know that one, because this is this right there. So what I end up with is omega 1k crossed with Lj plus omega 1k crossed with minus omega 1Li. This ends up being minus L omega 1 in the I direction minus L omega 1 squared in the J direction. So that's the velocity of the radius, or of the center of the disk as it rotates around O. But now if I want to do P, I have to do P in terms of where it is in relationship to A. So I'm going to get the velocity of point P with respect to A. Well, we know omega. And in this case, R is the radius of the circle in the K direction. Basically, we've said that this is the K direction. This is the J direction. And this is the I direction. When I play with that, this just simplifies to R omega 1 in the I direction. Finally, something that simplified into something manageable. I'm going to do the same thing for my acceleration. Now we've already done this one, so that plops in there. So this equals that's not K, this is I. So that's this term. And that's this term. So working through the math, which we can simplify just a little bit more. Excuse me. And now the velocity of point P is just going to be the velocity of A plus VPA. And when I take those two things and add together, I get minus L omega 1 I plus R omega 2 J. And AP is going to be my AP plus VPA, or APA. And this gives me minus L omega 1 dot I minus L omega 1 squared J plus R. I left out a dot when I wrote it there. I left out that dot. R omega dot 2I plus R1 omega 1 R2. I've got two of those in the J minus R omega 2 squared K. And when that simplifies, you get minus L omega 1 dot plus R omega 2 dot in the I direction plus minus L omega 1 squared plus 2 R omega 1 omega 2 J minus R omega 2 squared K. Like I told you, it starts to get a little gory. So we're going to look at another one. And I was laughing because we baled hay over the weekend. And I was watching how the baler worked.
That is hard work, like actually throwing hay onto a trailer. That
Yep.
is some really tough work.
Yep. I bucked it off the trailer. I didn't put it on the trailer. I was driving the truck to have somebody put it on. Okay, so I'm going to use this as an X coordinate, a Y coordinate, and a Z coordinate. We've got a part that's got a collar on it. Okay, and this collar is connected to a crank. And the crank, so as I turn this crank, so as I rotate this crank, this collar can go up and down. Okay? So I'm going to set it up so that my collar is at point C. I'm going to use a point P here. This is the place where this is connected. I'm going to put in a reference frame to help me out. Got my piece here. The end of the arm for my crank is Q. And this is 30 degrees below the horizontal. So if I'm adding some things to help me out, so I've got, this is 30 degrees below the horizontal, and the length of this arm is 0.2 meters. Okay, and the length of that arm is 0.2 meters. My arm that connects Q to C goes like that. It's 3 meters. And we're going to call this rod B. So I've got A, or P locates the pivot point for my crank. PQ is my crank arm. I have a rod connecting to C. And if I'm looking at, I'm going to use my blue to give me reference points. So you can kind of get your bearings there to help out to get your lever arms. We're going to be rotating at a theta dot of 3 radians per second. This initial angle is 30 degrees. The velocity of C is going to equal the velocity of Q plus the relative motion of CQ. And the velocity of Q is going to equal the angular motion of PQ crossed with QP. And RQP, when I use my angles and everything, RQP is going to be a minus 0.173 in the I direction, minus 0.1 in the K direction. It's staying perpendicular to the Y. I didn't draw it real peachy, but it's staying perpendicular to the Y. So I've only got an I and K component. And we're going to need it later, so I'm going to go ahead and write it out. RQC. RQC is a plus 0.13 in the I direction, minus 0.2 in the J direction, plus 0.1414 in the K direction. Which is why I drew the coordinate system to kind of help so that you can get your R's from the coordinate system. If you know that angle, you can get, and you know the length, you can work through to get those R's. So if we're told what omega PQ is, we're given that. The thing we are not given is the fact that that's going to be omega PQ is going to be 3. Oh, I'm sorry, that wasn't 3. It's 3.6. 3.6 radians per second in the J direction. So VQ is going to equal 3.6 J crossed with my minus 0.173 I minus 0.1 K, which is going to give me 3.1 I. No, it gives me 0.36 I minus 0.624 K. 3.6 times 0.1, J cross K gives me that. J cross I gives me K. 3.6 times that gives me 0.64 or 0.624. Okay, so VC is just going to be my VQ plus my VCQ. And I'm going to write out my VCQ in my vector notation. I, J, K. Omega in the X, omega in the Y, omega in the Z. And I've got to use my RC or RQC, which is my 0.173, my minus 0.2, my plus 0.1414. This is just omega cross RQC in its determinant form. So now I'm going to do my determinants, and I'm going to get the following. I'm going to get 0 is equal to 0.36 plus 0.1414 y, omega y plus 0.2 omega z. I get 0 is equal to minus 0.1414 omega x plus 0.1732 omega z. And I get VC is equal to 0.624 minus 0.2 omega x minus 0.1732 omega, I think that's y, should be a y. Okay, I don't know omega x, I don't know omega y, and I don't know omega z, and I don't know VC, but I only have 1, 2, 3 equations. So I got a problem. My problem is I got 4 unknowns and only 3 equations. I need another equation. Well, in this case, we're told that rod B does not rotate. So rod B does not rotate, which means omega of B dotted with RCQ has to equal 0. And omega B is my omega x plus my omega y plus my omega z. And I'm going to dot that with my 0.173i, my 0.2j, my 1.14k, which gives me 0.173 omega x minus 0.2 omega y plus 0.141 omega z has got to equal 0. And now we can solve the 4 equations, 4 unknowns, whichever way you want to do it. And you get VC is equal to 0.182K. Omega B is equal to a minus 0.98I minus 1.414J minus 0.8K. Yep.
I'm just stretching.
Okay. All right, one more thing I want to introduce, just so you guys have seen it. Let's look at angular momentum. And remember that H of A is equal to my center of gravity plus R cross MV, where R is my relative position vector, and this is my linear momentum of my system. But what we need to look at is what happens with my moments of inertia in 3 dimensions. And what we end up doing is defining what's called an inertia tensor. And if you guys remember, can you remember the only other place we've mentioned tensors?
I have no idea. I forget.
Is it vaguely familiar? We ended up dealing with something called a pointing vector. We mentioned it and said, you'll get to see this down the road, because we did phasor diagrams. I was in 2 dimensions, but when you throw a 3 dimension in, we can tend to get another tensor. Okay, so tensors become, when we start dealing with things that are happening in 3 dimensions. And what happens in 3 dimensions is we get those weird diagrams that we're trying to deal with. And we talked about being in 3 phase, and we talked about a few other things. So tensors actually show up. So tensors are kind of a weird thing, and this is why the BELT program says you want to do multivariable calculus, because you're going to end up doing these determinants and tensors and the three integrals. So we end up defining this inertia tensor, and the inertia tensor fundamentally gives us the inertia properties of a body about at point O. Okay? So it's really just giving us an inertia properties of about point O. So what we end up doing, if we're looking at our moments of inertia and going back and looking at our moments of inertia, we start with the mass moments. And our mass moments look like this. So if I'm looking at my mass moment of x in over some volume, I've got to look at the y squared plus z squared dm, because that's my r squared, right? If I'm looking at the mass moment of about x, I got to look at the r squared about x. So that's what that one is. And I've got the same for my y, except now it's x squared plus z squared dm. And then I'm looking at about z, and that's going to be my x squared plus y squared about dm. So this is just my I, but I'm using it in terms of r. Instead of r squared, I've got to deal with my x and y. If I'm using with my y and z, if I'm doing it, I got to use my x and z, and if I'm doing it, I got to use my x and y. Then we deal with what we call the products of inertia. And lucky for us, Ixy is going to equal to Yix, which is going to be my xy dm. And I'm going to do the same thing for the other two. And then our tensor just becomes this. So we get a big bold I. And then we can do our cross products, do our other things that we need to do, but I just wanted to introduce that tensor. And now I know brains are totally full. So I will see you guys on Thursday for the exam.
We survived, guys.
Thursday for the exam. You gotta get through the exam
Oh,
yet.
yeah, that's right.
Gotta get through the exam. And I went in and I think I sent out the note that I did go in, got the quiz dropped. So the grade, when the quiz got dropped, most people's grades jumped up again, which makes sense when I had the worst case scenario in there. And everything seems to be calculating correctly now. So I haven't added any more homework or any more things. We have 2 homeworks that are due today. Is that right?
No, we have one homework that's due tomorrow and one homework that's due the day after that. We also
Okay, so Wednesday I will go in and put the stuff in that was due on Tuesday so that you have everything in except for that last homework, so you know exactly where you stand. And Kay, did you get that? Cause since you came on late, that, we are not having class tomorrow because we have covered everything that we need to have.
Okay. Sounds good. Is the final 15% still? I was curious.
15%.
Okay. I saw in the grade book it was 200 points. I didn't know if that was.
No, it's 200 points. It's just to make it easy, you know, give you lots of extra credit or bonus points for partial credit.
Oh, okay.
Yeah. But it's only gonna be worth 15% of the grade.
Alrighty.
Yep, didn't change it.
Alright, thanks.
And I'll see you Thursday.
Alrighty. Sounds good.
And my notebook's heavy.
My bad facilitator, she started a group chat with all of us in it. Finally.
You started a group chat?
So they're dividing us all up into little groups with a certain facilitator, like 4 or 5 people
Yeah.
in a group.
All three of us got Cody except for Kristen.
Yeah. I got put with Randy and a bunch of other guys I don't even know, so
So is it just men in your group? And,
just guys.
and Randy?
It's
It had to be totally random then. I thought
what were
maybe.
the chances? I think it's because you guys didn't know all of the facilitators, but the fact that I went to the Second Ball experience, I met all of them, so
I
like,
think
yeah,
probably
we can see
true.
what's happening.
Because I figured maybe they